Dear all, welcome to our Translational Data Analytics speaker series. This particular event is co-hosted with Battelle Center for, sorry, my apologies. This particular event is co-hosted with Battelle Center for Science, Engineering, and Public Policy, and we're delighted to welcome Rayid Ghani from Carnegie Mellon University. I met Rayid for the first time in 2012 when he was the head of the Obama Analytics campaign in Chicago, and I was volunteering and trying to really come up with various ways of analyzing data to really improve the campaign reach and message and participation. And after trying every state-of-the-art machine learning and data analytics approach, I came back to Rayid kind of brokenhearted and said, I've tried everything and only the really simplest things work. And I remember Rayid looking at me and saying, that's great. You know, you're not writing a paper. We really want something simple and actionable. And so that message, that is something that I've learned over and over again from Rayid's work, from and teaching, because he has passion for both, of taking academic research and translating it into policy, action, impact in society, and really not only showing the difference, but understanding and teaching that difference between research and implications and translation and policy, and teaching it to everyone, bringing everybody into that conversation and into that process. He's been, well, Rayid calls himself a reformed computer scientist and a wannabe social scientist who aims to increase the use of large-scale AI and machine learning and data science in solving large public policy and social challenges in fair and equitable manner. And he has a passion for doing so and really acts on that passion, not only in research, as I said, but he works with governments and nonprofits and policy. And also he is the founder of the Data Science for Social Good Fellowship that trains computer scientists, statisticians, social scientists, and many other students from around the world to work on data science problems with social impact. Before joining Carnegie Mellon University in fall 2019, it's been a little, Rayid was the founding director of the Center for Data Science and Public Policy, research associate professor in computer science, and a senior fellow at the Harris School of Public Policy at the University of Chicago. And before that, he was the chief scientist of the Obama 2012 election campaign, where he focused on data analytics and technology to target and influence voters, donors, and volunteers. And it was the first really massive, intentionally data analytics enabled campaign at that scale. And with that, I am delighted to introduce Rayid Ghani and his talk on doing good with data science fairly and equitably.
Okay, thank you, Tanya, for a very generous and kind introduction. Yeah, Tanya and I have known each other for a while, and we lived in the same city for most of that time. And then COVID happened, so we left Chicago. Just kidding. Didn't leave Chicago because of COVID. But I think us leaving Chicago caused COVID because it happened after that. It must be causal. Anyway, so let me share my screen and try to keep you awake for the next 45 minutes or so. So what I kind of want to do for the next time is kind of talk about a few different projects that we've been involved in over the last few years, where We've tried to kind of have data play a little bit of a role in at least helping tackle social challenges with governments and nonprofits, and then sort of talk about sort of how some of those, not some, all of those projects sort of have issues around equity, right? So one thing, if you notice on my slide here, I give equal opportunity to every buzzword. So make sure that I have, AI and machine learning and add some deep words here and data science and fairness and equity. And so all the words are there, so nobody is offended by not missing their favorite word here. So let me start by sort of depressing people and giving some depressing examples, because that's kind of most of the work really involves really dealing with those types of issues. And as Tanya sort of saying, feel free to post questions, and I'll try to keep an eye out, but I think other people will as well, and happy to answer them as I go along with their clarification, but also leave some time at the end. So here's
I will monitor the questions,
okay.
And then we'll pass them on to you, Rayid.
Thank you. So here's a project that we've actually been involved in since about 2016. This is how long these projects take. It's still ongoing. So this is work in Kansas, in Johnson County, which is the border of Kansas and Missouri. Like the rest of the country, the criminal justice system, has issues, and most of us are familiar with that. The numbers that you see on the left here are just about jails in the US, right? So in a given year, 11 million people go through jails. It doesn't include prisons. And the horrible parts are kind of at the bottom, right? 2/3 of the people going through jail system have mental health issues and substance abuse disorders. And so these people keep cycling in and out. They come out, they have needs, unmet needs that are really, that the jail can't really deal with, doesn't help them. They come out and they go back in, and then they come out and they go back in. And so what the county team came to us and said, look, we've got a high recidivism rate. We suspect a lot of it is because of mental health needs that people have. We want to try to run a pilot where we have some resources to provide proactive mental health services. Can you help us figure out who to prioritize for that program? So we started with, okay, well, what do we know about these people? And work with them to get access to criminal justice data from jails, from prison, from police, from mental health services, from emergency room data, because a lot of those people also cycle in and out of emergency rooms, and ambulance type data. We kind of connected all that together. And the first thing we did was like, okay, we want to be able to do two things, right? We want to identify people who are at risk of going back to jail, but we also want to identify people who have mental health needs. So we started with kind of the more, let's build a system to do both those things. And so we built a machine learning model to predict who's going to go back to jail. Now, there are lots of issues there, right? A lot of ethical issues. We're going to sort of, the goal here was very much to use this model to intervene in a way to help these people, not to give it to the police. And we had a lot of those agreements already built in place where this wasn't going to go to the police. This was only going to go to the mental health services people. So we built that model, and we kind of, step one was to see how accurately can we predict that. And if it's accurate enough, then they can actually run a trial. So about middle of 2019, so June 2019, we started a randomized control trial, which was using this predictive model to evaluate the effectiveness of the mental health outreach given to these people. And we had sort of two goals there. One goal was we wanted to measure overall is, yes, we can predict who's going to go back to jail. Who cares? The goal is to improve their outcomes, not just to see them go to jail. Right? So the first step of the randomized control trial was, if we intervene with these proactive mental health services, does it reduce their risk of going back to jail? And second is, who does it work more effectively for, and who does it leave behind? Because if it's on average, it might be reducing recidivism by 10%, but it might be leaving certain types of people behind. It might not be effective for them. So we want to be able to identify that and then design new interventions for those people. So that trial started middle of 2019. And it's supposed to end this summer. And in the middle, COVID happened. So some of the, one of the good things that happened during COVID was arrests went down and jail bookings went down. And that's a good thing, but that's a temporary thing, unfortunately, right? So some of those things were interrupted, but sort of the early results I would just sort of share with you, we're just getting a couple of weeks ago, is we're finding that step one was to sort of see how accurately can we predict. And so this was sort of, in return to jail, and in the control group that we have, the highest predicted risk people, half of them came back versus the tier 2, tier 3. So unfortunately, or in this case, fortunately, we're accurate for these people. The more important piece is sort of this, is what our hypothesis was that, so the gray boxes are the control group, and the orange boxes are the ones
Right.
that
I don't think we're seeing what you think we're seeing.
Oh, hold on.
We're still seeing the first slide, yeah. The not the first slide, but the slide on reducing the number. Yeah.
So, you sure you're not seeing? Let me do one more. Are you still seeing the same slide?
Sorry. We're waiting for the slide to come through.
Slides are not moving. They're moving on my side. I wonder if there's a weird lag in the.
No, there were, but right now we're seeing black screen. So
okay.
Can you reshare again?
Yeah, I also, the slides are totally optional, so I don't.
Well, try resharing again, and also, of course they were fine right before the talk, right? I mean, that was not.
No. I mean, who knows, right? I unfortunately, I don't think I pay Zoom enough to. I think they charge you extra for a real-time refresh. Okay, you're still not seeing slides?
No.
Okay.
Let's leave it here and see kind of how long it will take.
They'll eventually show up, but I'll keep talking, and
yes,
I don't need to worry about it. So what we basically found was two things happen in our treatment group. One is that their consumption of mental health services went up, which was a good thing. Second was that their new arrests and new jail bookings went down for our control group. Or for our treatment group compared to control. That difference was much larger before COVID than after COVID. So that's whatever that's, that is something we have to kind of look at. But the second thing that we found that was really interesting was that our hypothesis was that we are able to, we wanted to sort of check and see what risk group can we change outcomes for the most. And it turns out we actually had the highest impact on the highest risk group, which to me is, we're still haven't kind of dug deeper into that, but that wasn't intuitive, because we're expecting sort of the highest risk groups are so hard to often change outcomes for, that we were kind of expecting the lower and middle risk to be kind of more effective. But it turns out, at least so far in the results we're seeing, that the highest changes is happening at the highest risk level, which is extremely encouraging, but something we have to dig deeper into. So that's that project. We're kind of a typical project for kind of coming up with sort of what the goals, the problem are, getting all the data, connecting it together, doing the analysis, building these models, and then running these randomized control trials to, when possible, to validate and evaluate the effectiveness, and then working on kind of deploying this system in these places. So if it's still not showing up, it's
not showing up. Can you email? So I don't know if it's a matter of screens or whatever, but if you can email it to Dev and me, we can advance it on your behalf.
Okay. Let me do that.
And as we're taking a moment to set that up, whilst you email, there's a question from Andreas Berland. So I'll read it out after you email.
Yeah. So the intervention.
When you're ready.
The intervention.
And now it's ready. And now it's showing. Fantastic.
I'll still email it to you anyway.
Yes. Yes, please.
Just in case.
Mm-hmm.
And so the intervention was there's a team of mental health outreach people who would do proactive outreach to about 100 people every month. So they basically would give them a list of 100 people who are highest risk of, who are stratified risk of recidivism and who we predict have mental health needs. And the team goes out and makes an outreach attempt. Before COVID, it was in person and followed by a phone call. Since COVID, they've been doing mostly phone calls. So that's where another reason for probably lower effectiveness since then is that the in-person component went away. But it's proactive mental outreach services as the intervention. So I just sent you the slides. Okay, so, and you can see them anyway now. Okay, so since we spent a lot of time on that, I'm gonna go through some of the other examples really quickly. Another project that we were working on for a few years, this was in Chicago, was around lead poisoning. And, you know, like a lot of cities in the US mostly are reactive about dealing with lead poisoning issues. They wait until somebody gets lead poisoning and they do tests. And when somebody gets lead poisoning, they try to kind of figure out how to solve the problem, which is a totally broken way of solving it because lead poisoning effects are irreversible. Once you have it, there's nothing you can do. So we worked with the city health department for several years to build a system to, again, to early detect, you know, kids who might be getting lead poisoning in the next 6 months. So it gives the health department time to go do lead inspections and then remediation to remove the sources of lead that are going to cause lead poisoning in the future. So again, we ran a trial with the health department with inspectors going out and testing, and now that system is deployed in the city as well as in a couple of hospital systems to basically look at, can we do this early when a pregnant woman is going in for checkups? The EHR system raises flags to identify, to sort of flag it, say this kid, it might be the kid that's going to be born is going to be at risk of lead poisoning. Again, I'm going through these very quickly. Another horrible, depressing police misconduct. Again, not isolated in any part of the country. It's in most places. And this is some work, again, we started in 2016, 2015, actually, I think maybe it's a little bit earlier, on working with police departments to build a system that identifies police officers at risk of doing horrible things that they shouldn't be doing. Unjustified use of force, unnecessary injuries, any other, you know, use of force type things, and firearms, and this system was, again, looking at all the information that the police department has about an officer, their history, their training, their dispatches they've been sent to, arrests they've made, complaints against them, like other types of things, and using that to predict risk of doing something horrible in the next 6 months or 12 months, and then providing that information to their supervisors so they can, or to the department so that they can intervene. And you know, the interventions are sort of different types, right? Some of them are as simple as taking them off active duty and kind of putting them on desk duty. Some of them are more training interventions. Some of them are a little bit more nuanced. So a couple of predictors we found that were kind of coming up were things like repeated dispatches to suicide attempts or repeated dispatches to domestic abuse cases involving children, which are kind of proxies for stress. When they were being sent to those types of dispatches repeatedly, they became high risk of doing other horrible things in the near future. And that's where the intervention, there's sort of two types of interventions that we're looking at. One is, don't do that repeatedly, kind of once somebody's been on there, stop, you know, give them a cool down period. But also the couple of departments we worked with, you know, one of them hired a counseling team to see if that would reduce their risk. So that system has now been deployed now for a couple of years. And one of the things we're in the middle of is getting that data back from those departments to evaluate and see how, if it's, what impact it's having on again, uses of force and injuries and all the horrible things that have been happening. This is, you know, there's a lot of work in this area of identifying students who need extra support in order to graduate high school or time, or get to college, or match to the right, you know, not under match to college, or get to third grade reading level on time. And I think that so this is some work we've been doing in different school districts around the country, most recently in El Salvador, but also an active project going on just to sort of southeast of you guys in kind of southeast Ohio in Muskingum Valley, where we're working with a set of school districts to help them figure out how to improve college admission outcomes for some of their students in a way that they can do early interventions. You know, it's very easy to predict who's going to graduate or not graduate, you know, the minute before they're supposed to graduate. It's much, but not actionable. And so the idea here, like, you know, can we predict things early on and support interventions in a way that can reduce some of these adverse outcomes. I'll kind of skip through some of these. Here's an active project just to give you an idea. This is some project that we've been doing with Mexico over the last year, unrelated to COVID Act. Well, this is more around children vaccinations in general. There's a large percentage of kids who don't get vaccinated, not necessarily for the crazy reasons that you know, US people don't get vaccinated. It's a lot of it is access, a lot of it is supply. Sometimes there's no supply available. Sometimes they don't have access, transportation access, other issues, reminders, things like that. So we've been working with them to develop a system that can identify the high risk children of not getting specific vaccines, and then again do sort of proactive outreach. So it's an ongoing project that right now we're in the analysis and modeling phase, and we're kind of getting ready to do a trial, ideally over the summer or in the fall. There's a lot of projects that we've been doing around inspections, and so one project in Chile on supporting, trying to figure out, you know, it's sort of a common problem in inspection is you've got this many, this is for workplaces, right? So ranging from offices to coal mines, and the labor ministry there has thousands of these workplaces to inspect first to make sure that they're complying with, you know, safety standards, but only has resources to inspect a few thousand. This is the same with, you know, EPA that has a few 100,000 facilities to inspect and make sure they comply with hazardous waste regulation laws, but only have resources to inspect a few thousand again. And so the question is, how do you prioritize those? And a lot of it is a matter of deciding, what is your policy goal? Do you want to be efficient, where if you do 4,000 inspections, you want to find 4,000 problems? Or do you want to maximize deterrence? Because who cares how many problems you found? You want to minimize the problems in the larger set, not necessarily in the set that you inspected. So there's some interesting kind of questions there. Let's see, I'm going to actually a couple of more examples. This is some work we did a few years ago in Syracuse, New York, around water pipes. And again, I'm, you know, not the most important problem in the world, but we all experience sort of water pipes breaking. Yes, they're inconvenient to you know, navigate around if you live there, but also shuts down your water supply. It affects grocery stores, can't sell, you know, anything frozen or refrigerated, and it's expensive to fix, because unlike other things, you have to sort of dig up the street, fix the pipe, put it back together. So they have, you know, small town Syracuse, they have about, you know, a break every other day, right? So 180 breaks a year. So they wanted us to help them figure out which pipes are likely to break at different points into the future. And the interesting thing here, the reason I'm mentioning this is, unlike some of the other projects where you predict something is going to break and you sort of preemptively try to fix it, or you predict the student is not going to graduate, so you try to connect them with after school programs. You predict this kid is going to get lead poisoning, so you try to remove the red lead. Here, the goal is not, I'm going to predict a pipe is going to break and dig up the street tomorrow and fix it, because it's kind of expensive. It may not be needed. So what they really wanted to do was use the risk scores to coordinate with the the roadworks department to come up with a plan for redoing the streets. And while they redo, if a road was going to be redone in the next 6 months and it came up as high risk of the pipe breaking there, they can move that schedule up. If it's a lower risk, the medium risk pipe, then instead of opening it up and fixing it or finding it's not broken, they would then prioritize it to kind of put in sensors so that they can monitor those for water leaks and kind of. So that was a different type of intervention. Instead of going and fixing things, it was really a planning intervention using the risk scores. One last example. This is some work we're doing in Jakarta in Indonesia on traffic deaths. So a few thousand people die. Yeah, so there are some questions around bias. The second half of my talk is going to be all about the bias. So just give me a few minutes and I'll get there in more detail that you probably wanted to know. So this is on traffic. The few thousand people die every year of traffic accidents. It's pretty bad. And so the city there, they, like any other smart city, they thought, well, if we only made it a smart city and put a bunch of cameras, it will stop all these deaths. So they put in a few thousand cameras. And unsurprisingly, after a couple of years of that, they came to us and said, well, we put in the few thousand cameras to figure out why these traffic deaths were happening. And we just now have thousands and thousands of hours of video footage, and we don't know what to do. So can you help us figure out? We don't really want, we don't want to predict something is going to happen. We would like to understand the root causes, but the video is not, just too much video. Can you help us structure this video into some sort of a spreadsheet and database that sort of just tells us what types of events were happening that led to an accident in the future nearby? So they kind of wanted to know things like, there are non-vehicles using the road, right? So this is like a food cart vendor or pedestrian crossing in the middle of the street or car driving the wrong way, or a motorcycle, all fairly normal things in the majority of the world. Wanted to kind of detect these types of events and where they happen and when they happen, so they could then look at what correlate them with accidents that are happening nearby in the near future. So the first thing was, a lot of these things sound really simple, and there's a bunch of off-the-shelf, computer vision models that are supposed to detect all these objects, right? Except they're all designed and trained on typically US traffic, right? So there is no category for non-vehicles like a food cart vendor. There is no category for, I don't know what the word motorcycle. And so we had to kind of customize and adapt things that were developed. One thing, just for people who were interested in this type of work, the typical these image models didn't even work to detect buses when applied to London buses, right? They're just so different in shape that we had to kind of adapt them for those types of things as well. So what we ended up doing was kind of doing that and then detecting different types of these objects, tracking which direction they're moving in and where are they moving. Are they on the road? Are they on the sidewalk? Are they in the middle of the street? All those different things to basically come up with something that kind of tells us something like this, right? So what this is telling, this is a two-way street, but we sort of keep seeing, cars coming around and going through, and within a few seconds we see, and in this area we see repeated risk of accident. So that's kind of one pattern that comes out. And so in this case, an intervention might be putting in a median, in the middle of the street to stop that from happening. That will reduce the risk of those accidents. So it's kind of an example of again, the goal wasn't about doing predictions and building these models. The goal was really to give them the data they need in order to better analyze what they're trying to do, which they couldn't do with the raw videos. Just like a lot of the work that Tanya works on with wildlife things. So on all of these examples, right, especially one of the common themes, kind of, if you sort of abstract back to what these systems are trying to do, right? None of them are autonomous systems. They're not making automated decisions that are affecting anybody. They're supporting humans making decisions. They're supporting Police departments trying to figure out which of their officers are going to be high risk, and then supporting interventions, supporting Johnson County and trying to figure out where do I allocate, who do I connect with mental health services to reduce their risk of recidivism. It's supporting, all of it is really, it's these collaborative systems where humans are doing something, and our job is to sort of build these systems to help them make decisions, not automate. The second thing is, in all of these cases, we have limited resources, which is an unfortunate scenario. Ideally, we would have resources for everyone who needs lead remediation. We would have resource for everyone who needs mental health services. We need resource for everyone who might be at risk of not graduating from high school. But we don't. And while we have to fix that problem, and that's a policy problem, and that's getting better every day. Today, the case is a lot of the cities, counties, states have limited resources. They have to figure out how do they allocate them. And because of that limited resource allocation setting, we sort of have different goals. We want to make sure that we are sort of balancing these goals of, we want to do it in a way that's equitable, and balance it with sort of efficiency, because we still have limited resources, and also have effectiveness, right? So one way to kind of think about it is a lot of the times the framing that a lot of these problems have is, we want to help the most number of people with the resources we have. Well, that is an efficiency framing. That's basically all I care about is efficiency. I want to help as many people as possible, which means that you're going to sort of help the people who are cheapest or easiest to help, because then you can help more of them. And that means you're going to leave people behind who are harder or more expensive to help. And that's going to result in inequity. And so these goals, pretty much every project I talked about, we sort of have this conversation upfront about how do we design the system that, that sort of gets this, where equity comes first. What does it mean to sort of design it as come up with this goal? And then how do we implement it into the technical system, into the objectives of the system? When we're building these machine learning models, we're not sort of just building it. There's no such thing as a generic machine learning model, right? It's you're tuning it to do something. And if you don't tell it what to do, it basically tries to get as many predictions right as possible, which is another way of doing efficiency, right? So that's kind of the idea here, is that in all of these projects, we want to sort of figure out, how do I design a system that is really focused on achieving equity rather than efficiency? And so the process that we take here in all of these projects is, we first sort of even start with thinking about, what do we mean by equity in this case, right? And here I want to make sure that I'm not talking about sort of the machine learning model necessarily being fair or unfair, because you could have a totally fair model resulting in totally unfair outcomes, right? So take kind of the lead poisoning example. You can have a model that's perfectly fair, and now the way it's modeled to be used is to call the parents of this child that you just predicted to try to make an appointment to do an inspection. Now, initially when they started doing it, they were making these phone calls in English. Now, if your model is totally fair, but now your outreach is in English, the outcomes, there's no way the outcomes are going to be fair. You're going to miss out on all the people who don't speak English. And so a perfectly fair model is not enough. Same as you can have an unfair model, but you can mitigate the risk, the unfairness risk of that model by intervening on more people from the group that you're being unfair to. And that can change the outcomes to be more fair. So one thing that we've been looking at is, we care about the overall system and outcomes being fair, rather than just a component of your overall pipeline being fair. So we kind of start with thinking about, what do we mean by equity? And because you could have a lot of different definitions, we need to have, and if we don't define it, it's going to be hard to actually design a system for it. Once we've defined it, how do we measure issues of bias and detect bias in different components, again, of our system? How do we understand the root causes? How do we improve as much as we can? But then wherever we build, it will have some inequity or unfairness in there. So how do we mitigate its impact, and then how do we monitor and evaluate, right? So what we start with is thinking about, where does bias come in, right? And typically we sort of often jump to the data. It's like, oh, the data is biased. Like, well, yes, the data is probably biased, but the world is biased. And that's kind of the root cause of a lot of these issues, is the world is biased, the world is sexist, the world is racist, and that generates behaviors, that generates data, generates everything else that have the same thing embedded in them, right? So that's kind of, a lot of the bias comes from the world. Then a lot of the bias comes because the data gets generated, right? So the data might not capture everyone, and most data sources are kind of that way. They have a huge sample bias. Social media is a perfect example. It is not representative of most of the world, right? But we also might have biases around how accurate data is about different types of people. A lot of survey data has those types of biases where you might ask certain, depending on how you ask the question, you might get different answers. The outcomes in our data are also sometimes biased, right? So the example there a lot of kind of the most sort of example, the one that we ran into quite a bit was, if you took a look at the police example I was giving, in this case, the machine learning model we're building, the outcome we're predicting is an unjustified use of force. Now, if you're a police department, every time a use of force happens, an internal affairs investigation gets started. If you're a police department who is totally corrupt, not saying any names, but lots of large city police departments are that way, you will never call anything unjustified. You'll investigate a case and say, nah, that's fine, it's justified. And so now the machine learning model you're building, it's not going to magically figure out that what you called unjustified was actually justified, or vice versa. So it's going to have this huge bias of, well, things are nothing is unjustified. So it's never going to predict anything that's justified in the extreme case, right? And so that's a huge bias. But even in the other case of students graduating from high school or not, you might consider that as an objective ground truth outcome, but that's not an outcome. That's an outcome that happened to that student, but maybe because the school didn't have the right support programs for them in order to help them graduate on time. So it's not about the child, it's about the context of that student, the support that they needed, and the support that was provided. That's what's generating that outcome. So when we're building these models, all of that is embedded in there. It's really hard to kind of separate out, right? The third piece is sort of totally our fault as people building these types of systems. We make a lot of mistakes. We make a lot of assumptions. We embed a lot of biases, and that results in bias creeping into the system. And the last piece that was talked about is actions, right? How we use the system is also biased. Outreach programs, if you're doing it over phone calls, then you might be biased against people who are hard to reach over phone. If you're doing it in particular language, it might be hard to get people. If you're doing it on certain platforms, online only or mobile apps, you're going to miss out on people who don't have access to it. So the idea really is to kind of focus on each component and see how do we deal with that, right? And just to kind of give you an example, sometimes very simple, sort of innocent sounding things result in pretty big impact on bias, right? So for example, this piece here on actually the first piece here on getting data, like when we build these systems, we sort of make choices about what data sources to use. Each data source comes with its own biases, and by choosing certain data sources, we're already sort of embedding our own bias about, oh, I don't think I want to use this because it may be biased. Well, maybe we're wrong, maybe we're right, but that's a subjective choice we made. Even sort of this little thing like, record linkage, when we're linking people together, we sometimes miss people who should be linked together. We sometimes link people who shouldn't be. And people, with long names, with lots of consonants next to each other, tend to have more typos, and they get missed. People with common names living in main streets tend to get linked together. And you can sort of argue that yeah, that's an error, but it's not a random, uniformly random error. It affects different people disproportionately. But downstream, by missing people, you've kind of removed events about them from the data that you would have known about, and linking people when they shouldn't be linked. You're connecting other people's outcomes to them, possibly that didn't happen to them, and that leads to biases. Even simple things like missing value imputation, where we might, let's say our data set is 80% men and 20% women, and we have some missing attribute about a woman in there, and we say, well, let's just do mean imputation, and we'll come back and figure it out later what the right thing is. Well, mean imputation means, let's say you're missing somebody's height, you're going to take, you're now going to have this woman look more like male because you imputed based on the whole data. So very simple, and that's going to result in predictions about them that are going to be biased. So very simple, kind of innocent sounding things have implications downstream on the biases that get introduced. So we've kind of be very thoughtful about each step and say, okay, what decision am I making in this step? What are the implications of this decision 3 months later, 6 months later, when the system gets actually used? And what can I do now that can kind of help me be more aware of other choices I can make, document, have a discussion, figure out the right thing to do, as opposed to making an ad hoc choice. So once we've kind of thought about some of those, the next question becomes, well, how do we figure out what are we measuring, right? And over the last few years, people have sort of proposed different types of metrics in a very narrow kind of machine learning model side of what different metrics for kind of biased, right? And generally there's sort of two types. One of them is around sort of distribution, right, of who you chose to intervene on. And so there's sort of, and people might say, well, we want equal percentage of Black people and brown people and white people. Or I want to make sure that at least that the, of all the people who needed some support, 10% of them are from each group, or so there's some of these distribution type measures. And then the other ones are all about error rates. So we made mistakes. We either, predicted somebody to be, high risk when they were not, and that's a false positive, or we missed somebody when they should have been high risk, that's a false negative. And so each of those errors, if it's disproportional across race or gender or urban versus rural or age, could have impact on people. And so there are all these different metrics, and the question becomes, which one metric is the right metric? And there are sort of lots of, there's been work done on what are the trade-offs here, but also, some of the incompatibility type things of if you want to have equal false discovery rate, then you can't have, other metrics. And one of the things that's coming out of that is that, well, of course, it's very dependent on what you're going to do with the system, right? What is it that you're going to use it for? So one of the things we did was we developed sort of this thing we call a fairness tree, which helps this is really more from a policymaker side, helps them figure out which metric matters for them, because they don't need to worry about all the metrics for each type of problem. You one metric is more important than others, right? So for example, here's kind of a zoomed in version. If your interventions that you're doing using this model are going to be punitive, that they could hurt people, then you mostly care about, not having disproportionate false positives, because a false positive is going to be much worse if your intervention is punitive. And there's more details here, but I'm going to give you a high level view. If your intervention is assistive, right? If you're providing mental health outreach programs, so all the examples I gave were really assistive interventions, then missing people will hurt them. So if you miss certain groups disproportionately, then that's going to be much worse for them than a false positive, because false positive is, yes, there's an opportunity cost and some efficiency issues, but in this case, we really care about helping the people who need the help. So that's kind of an example of helping people who are really on the policy side not get kind of overwhelmed with the machine learning metrics and papers saying, well, you can't achieve all of them, because then they get to the conclusion, oh, we can't get all of them. So that means machine learning can't be fair, which means we shouldn't use machine learning, which means we should continue to make decisions in the wonderful ways that we've already been doing, which is totally fair and totally non-racist and non-sexist and, you know, totally right. And that's not where we want to get to. Right? We want to sort of get to somewhere which is more reasonable than where we are today. And these types of systems, I'm going to show some examples of, can be used to actually get us there. So here's, you know, once we've defined what metrics we care about, we at a minimum want people building these systems, especially for kind of these high stakes decision-making things, to at a minimum audit their tool, that audit the system that they've just built, so that they don't just blindly use it and find out 2 years later when some newspaper or journalist investigates them. They should be able to audit and ideally be required to release the audit results before they deploy a system like this. So here's a simple, very simple tool we built a few years ago, which takes the predictions of the model and asks, you know, what groups do you care about? And helps you go through this, the fairness tree, and say, what metrics do you care about? And then audits the model to show you it is biased for this group. It has three times higher disparity in false discovery rate. So now you have to decide, if you're going to use it, you have to justify why it's reasonable to use it, even with this disparity. And so that's kind of something we've been pushing a lot of government agencies, and they've been kind of running some of these. All of our projects go through these audits before we even put them in trial. And at a minimum, what it's sort of helping us do while building these models. So they're kind of, the question is, you know, how do we build them to be more fair? And one way of thinking about it is, this is kind of the standard thing we do in a lot of machine learning type work is, you know, we have some performance metric. Now, ideally, this performance metric is sort of relevant to the problem you're solving, but you still sort of, you know, you say, okay, I'm going to pick the yellow one because, you know, it's the best. And so what we're saying is, at a minimum now, instead of doing this, we're going to add one more dimension, which is sort of this disparity that we've just figured out. And now the yellow one is still the best on this axis, but maybe this green one is a better choice, because it's not, you know, you're giving up a little bit of this performance, but it's much less biased. And so this is kind of an abstract view, but let me kind of make this more concrete, right? So here's, I'll let you skip this example and give you this is some work that we were doing with a set of clinics in Chicago around diabetes screenings. And one of the things about, so there's this federal task, it's called US Preventative Services Task Force, and they have these guidelines for when somebody should be screened for diabetes. And they're mostly based on age and BMI. Except, like most things, it's based on data from white people. So it covers white people very well, but it under predicts and underdiagnoses minorities. So this clinic came to us because a lot of the people they were serving in Chicago, the set of clinics were, you know, were not white. And they said, well, can you help us develop a better way of identifying who do we screen? So basically they wanted to, can you help us identify who's going to get diagnosed with diabetes? And can you tell us, because ideally we want early enough predictions so that we can actually do something about it. And kind of managing diabetes or preventing it requires big lifestyle changes that they said, look, they take a ballpark, you know, a few years. So we need something that's ideally giving us a 3-year early warning so that we could do something about it. Because if you give us 3 months before, we can't fix anything, we can't change it. So we kind of looked at this problem and said, okay, we want to build a system that's giving us accurate predictions and more importantly, equitable predictions for early diagnosis of diabetes. And so the first thing we did was, you know, actually I'll skip through some of this stuff. We sort of looked at their current system. The physicians in that clinic were making the same prediction, right? In their head, they're saying, this person I think is going to get diabetes, so let me screen them. So how well are the humans doing? And this is how well the humans were doing, right? basically the y-axis is the error rate. It's like what percentage are they missing? Because this is, again, an assistive intervention. So we care about not missing people. And so we find that the human physicians are, are pretty bad at 40-plus-year-olds, and they're pretty bad at Native American, Native Hawaiian. They're about equally right for male and female. So then we said, okay, let's build a machine learning system. And the first iteration of it was just purely based on let's get as many people right as possible. And here is the blue model. The blue lines are for that machine learning model, and the lower the better. So lower is lower error. Right. So what we find here is two things. One is kind of obvious. The blue line is always lower than the orange line. So for every single age, gender, race groups, this overall model, machine learning model, was better than the current humans. And we actually find that repeatedly is in a lot of these things that we can do better. But there's a catch. If you sort of notice before that the physicians were equally bad about 40 to 70 and 70 plus. Now there's a disparity. This machine learning model is more accurate for 40 to 70 and less accurate has higher error for 70-plus-year-olds. So what it's basically done is it's made things better for everyone, but it's introduced disparities. And those disparities could be societally really important because they could have longer term implications. So then the question, and then again, that's a policy choice to decide, like, what do you care more about? Improving things for everyone on average or reducing disparities, right? So then we said, okay, what if we built a model that was, in this case, we've also found that it had a higher error rate for some of the races. So what if we built something that was optimized for Hispanic population? And so this light blue is the one that's the best Hispanic model. And it turns out, yeah, it's better than the physicians. It's better than the generic model, but it's at the expense of the Native Hawaiians. And it's at the expense of, some of these unspecified ones. And so, okay, so that's another option. But what if we built something that's performs equally across all races? So how do we make it kind of more uniform, right? So this mustard colored model is that one. It's sort of about the same across all races, but in order to do that, it had to do worse for Black people and Hispanic people, Native American, and it does better for, so it has a higher rate of error for some, so it's sort of, we're kind of reducing something, we're increasing over here, and all of these are sort of somewhat ad hoc choices we're making when it's not, it sort of can be a little bit more principled than that. So we kind of did some more stuff there, but I want to switch over to a different project where we did that in a much more principled way in the next project, right? So this one was a project with Los Angeles where they were, this was the Los Angeles City Attorney's Office, where they, very similar to the Johnson County, Kansas example, there were people who were kind of they kept cycling through the system through misdemeanors. And what they needed was really diversion programs and social services interventions, and not put them back into the system and cycling around, except they didn't have enough resources, again, to focus on all of them. And so they came to us and said, look, what if we sort of prepared the right plan for, we have enough time to prepare a plan for about 150 people a month. Can you help us identify those people, and not just efficiently, but also in a way that's fair, right? So what we did was we sort of started with building a model that was, again, the most accurate model, which again relates to efficiency. What we found was that model was 73% efficient. That means that of the 150 people we identify, 73% of them do come back and get arrested, so that if they prepared the case files for them, they would be 73% correct, right? They would be useful for 70% of the cases. Now, what was interesting was that that model was more accurate for white people than it was for Hispanic people. And as we looked at that further, we saw that the Hispanic recidivism rate was much higher than that of white people. So basically you're starting with Hispanic recidivism rate, white recidivism rate. And now if you take your interventions based on this model that is efficient, but more so it's helping both groups, but it's doing it more efficiently for white people than Hispanic. So both recidivism rates go down, but the white one goes down faster than than Hispanic. So essentially what it's resulting in is this efficient model that's disparately efficient for the two groups is reducing, just like the previous, it's reducing recidivism rate for both, but it's increasing disparities. So we said, okay, how about let's tune this model to be equally correct for both. So that means we're designing for equality. That ended up being 2% less accurate, 2% less efficient, but it was equally correct for both. What happens with that? Well, starting point is the same. It reduces the recidivism rate for both, but it reduces it equally. So it doesn't increase disparities, but it also doesn't decrease them. It just propagates the existing status quo disparity. Right. So we said, okay, what about number 3, which is let's design for equity, which is about the same cost as equality, and now it's helping Hispanic people with a higher recidivism rate at a higher rate than white people. And what it's doing is reducing these disparities such that, the recidivism rate becomes equal X number of, 7 years, 8 years down the road. Right. So that's the policy menu that we presented to the city attorney's office. Like, you have 3 options. You can go for efficiency, and here's the outcome. You can go for equality, and here's the additional cost, and here's the outcome. Or you can go for equity, where here's the cost and here's the outcome. In the back, there's a lot of, in their paper that I can point to that we have where all the math and the algorithms and all that stuff is there. But for policymakers, that was the menu that they needed to understand, as opposed to all the metrics and the machine learning things. This was kind of what, and they chose, number 3 makes a lot of sense for us. It's 2% less efficient. The outcome is what we care about. And so they decided to sort of use that model, but it's going to translate between what's possible to the outcomes, and then designing that system to kind of get us there. So I'm going to just wrap up by showing you sort of 2 things, and then I'll stop. One is, what we sort of notice is that we can get from inequity to equity by very little cost, right? It's 2% is minimal here. And we actually found after that, we sort of replicated that type of analysis on all the previous projects and said, how if we tune these models to be more equitable, how much accuracy loss do we get? Because in a lot of, if you've been to sort of machine learning talks and kind of fairness, a lot of people will sort of assume and imply there's this trade-off between accuracy and fairness. And we actually found that empirically on real problems like the ones we're talking about, it's not a general purpose, but empirically on these real problems where you have limited resources, you don't have to sacrifice accuracy. So basically this graph is very recent work. It's still under review in a paper. The U models are kind of the initial accuracy, enhancing things. And then the ones under it are the ones when we do corrections. So basically we have this model that's x-axis is accuracy, y-axis is disparity. One is really good on disparity, right? So first project, we get from 3.5 disparity to 1 without losing anything in accuracy. Second model, we actually enhance accuracy and get the disparity down. The green one, again, we go down from 1.5 to 1. The orange one, they're all the different projects. One is the student one is the criminal justice one, another one. So we find repeatedly, empirically, that there is no trade-off. But that doesn't mean that you can just build a model and hope that it works. So this is the criminal justice, the Johnson County example. Blue is the model we built originally. So if we didn't think about fairness or bias, we get a model that's not fair. If you some people will say, well, you shouldn't be using race. If you just remove race, it'll fix the problem. No, it doesn't really do that. So here, if you actually remove race, it gets worse. It gets more disparity. Or some people will say, well, if you just sample the distributions and oversample the data so that the smaller classes are represented equally, that'll fix it. No, that doesn't do that either. And then there are these methods that are for regularization, where they basically say, I'm going to add a penalty function if you have bias. Also inconsistent results. Some people will claim, well, you can build separate models for white and black and brown and Asian. And sometimes it works. In this case, it helps, but not as much. But we find that this sort of post hoc adjustment that we've been working on consistently does that across a lot of different projects. It's still early results. So this is kind of very early. It has been published. It's under review right now. But we basically, the key point here is that it's not just building a model makes it fair. You have to be very deliberate about designing for fairness, coming up with these metrics, and then coming up with the methods that are explicitly trying to get there, rather than kind of hoping that you get there. So yeah, that's kind of all I had. Basically, I think what we're finding is that a lot of the data buzzwords, these methods, they are giving us ways of designing sort of policies that are more personalized, individualized. And historically, they've been really focused to improve efficiency. But now I think we're finding that, they have the potential not to just sort of help, but actually help make things more equitable. But we have to kind of design, we have to have them be primary goals in our systems that we develop. It has to kind of come from the beginning, it has to be measured at each step. And then, the focus isn't and shouldn't be the model being fair, because the model is just part of the pipeline, but the overall system. And at least, I'm hoping that people consider sort of these types of collaborations that we've been doing with governments and nonprofits as a way of both helping have impact, but also focus on sort of research areas that come up that are kind of focused on more positive and equitable impact. So that's kind of all I had. I know I went 5 minutes over. I apologize. Happy to take questions now if people have time. Otherwise, also feel free to, I'm easy to find. So feel free to email me. And then code for everything I've talked about is on our GitHub repository, open source.
Thank you, Rayid. That was a blitz overview of a lot of work, which is fantastic. And thank you for also providing information about how we can how people can get access to code and all the other information. There are a couple of questions. The most recent one is
we have the significance person here.
Yeah.
Oh, sorry.
Yes.
They are all statistically significant. There are more details. I'm happy to send you the papers and stuff. More importantly, they're all practically significant. That's kind of because for us the bar is not statistical significance. It's actually, some of these things may not be worth implementing because they might cost more than help. So, but in all of these, at least we're finding that the reduction in disparities are, so what I showed was just sort of one graph with one project, but we're actually finding across multiple projects. And I'm happy to sort of, if you email me, I'm happy to share the paper with a lot more details and graphs.
So for those who are still on the webinar link, please do feel free to type. We have some time to do the Q&A session. Please feel free to type your questions in the Q&A box. We'll also follow up with a recording and posting, and you'll see other people's questions answered. But we have a lot of comments about how great this presentation was. So again, thank you, Rayid. I have a question while we're waiting. So, well, there's a question from Sam Malloy from Battelle Center. What are some of the challenges you have encountered interacting with policymakers in this work?
You should ask the policymakers this question, interacting with people like us. No, so I mean, there are a few challenges here that, a lot of people in the policy world, they may or may not know what's possible to do with these types of methods and techniques and technologies, because the examples they hear about are really examples that are more from, large tech companies and sort of big organizations with the resources. So they're not really familiar. I think what they're struggling with, they don't know what's possible. They don't have enough use cases and case studies. And then they don't necessarily have sort of things that are targeted for them, right? So one simple example, the one I was talking about, there are all these different measures for bias that were being proposed, and one of the conclusions that was coming out of it was, well, you can't get all of these different measures. So because they weren't translated for policymakers, a lot of the people I talked to said, oh, I read this paper and it said that you can't get fairness. So what I was saying is that the conclusion they reached was we shouldn't use machine learning tools because they can't be fair, which is the absolute wrong conclusion to reach. Or and same for, when there's sort of a lot of translation gap, which means that a lot of us sort of who are on the more the machine learning side of things, or the data side of things, and our side of things, have to learn how to communicate with them, and they have to learn how to communicate with us. And so that's a lot of other stuff that I do, is a lot of training classes for government agencies to help them be more, some of them actually in collaboration with Ohio State as well, for people in the state government. But I think that, and that's just one example of challenges. Other one is, I think there's a history of a lot of sort of computer scientists going to governments or saying, can you give me your data so I can test my new favorite method that I just developed, and in return they don't really get anything, right? So they've been burned enough times by researchers coming in and not understanding their problem that they're a little bit skeptical and wary. So you have to sort of in order for them to trust you, you have to kind of spend the time to do something useful. You have to care about solving the problem. But those are kind of some of the things. Yeah, let's see the other question.
Yeah, so there's a follow-up from Walid Mohana about the data bias. So Walid says, correct me if I'm wrong, but it is the takeaway that the bias in data generating process is immutable, and that the best way to address this potential bias is through post hoc adjustments.
Right. So that's, if I was giving this talk to a computer science department, I would have really gone down that path. And I try to keep it broad, but basically there are three methods to deal with today on the narrow modeling bias, right? One is people do it kind of what's called pre-processing, right? Where you modify the data, remove the sensitive attributes, sample. Second is in processing, which is you design your method. Regularization is one approach. The third is post-processing. Once the model is built, can you adjust things? In our experience, so all of these haven't been studied very carefully, just that big caveat, right? I haven't seen any extent. We just actually submitted a paper with comparing all of, a sampling of all of these on these real problems. And it was the first, because we were testing them, and it turns out what we found was the results were inconsistent for everything except for that post hoc correction one. We found that was consistently getting us to much more, reduced disparities than others. Now, again, that's not a proof. So, and it's on the class of problems that I'm talking about here, which is this limited resources, top K prediction type problems. So that's, yeah, but happy to sort of share with you the write-ups in more detail. There's another question on the John Sendel Manish paper. So that's exactly what I was.
I just, if you can go ahead and read the question, but just making sure that.
Sorry, yeah. So the question is, there's a paper on inherent trade-offs in the fair determination of risk scores, which is John Kleinberg, Sendel Malinathan, and Manish Raghavan. That was from a few years ago. And they're saying, what do you think about its conclusion? And basically, that paper says that you can't have, there's no controversy about the findings of that paper. It's basically saying the equations for these metrics are, if you don't have equal prevalence in different groups, so let's say your recidivism rate for white people is different than recidivism rate for Black people, if you want false positive parity, you can't have false negative parity. That's just how the math works. So that's a really useful paper. But what we're doing is saying true, but that doesn't mean that both false positive and false negative parities are equally important in a given problem. In some problems, the false positive parity is much more important. In other ones, false negative is much more important. So what they're showing is a theoretical result, which is very useful. It's really good work. And what we're doing is saying, okay, let's now figure out the policy implications of that result. And then there's another question.
So there's a question from Jen Wang. So that previous question was from Elizabeth Newton, the director of the Battelle Center. This one is from Jen Wang. Are there some scenarios in which fairness isn't the first priority to consider, but just a bonus? How should we deal with such scenarios? And do you have a principled way to inject fairness into existing deep learning models?
So it depends on how snarky I want to be. I don't imagine the problem where it's a bonus, unless it's a thing that's just sitting on your computer and not affecting any human being in any way, or even, I guess, animals for some people. Because if the model is just on your computer, then who cares if it's fair or not? But if it's an action is going to be taken and it's going to affect somebody in the world, fairness better be a consideration. So I would kind of think a bit more about, like, what are you going to do with that model? If it's a classification model, even there's a lot of work on word embeddings, right? And you can sort of say, well, it's just word embeddings. Who cares if it's fair or not? Well, a lot of companies are using word embeddings to analyze resumes and job postings and match people with jobs and suggest to recruiters who the top candidates are. So if your word embeddings are biased, and then it results in biased recommendations, which means people who might be qualified for jobs might not get interviewed. So that's the piece I would think more about is, what is my analysis? What action is my analysis informing? And bias in my models, how will it bias the actions that are being taken? And then to your point of sort of how do we make the deep learning models fair? That's kind of one of the reasons I'm a proponent of the post hoc correction things, because they're a little bit model agnostic, where your models are going to give you a ranked list. And it doesn't really matter if it's a regression model or a deep learning model, or a random forest model. You can do post hoc corrections regardless of that. Now, it's not guaranteed to give you something, but it's kind of the most model agnostic way, and fairly efficient for certain metrics. Like we find that to achieve recall parity, because recall is sort of monotonically increasing, we can actually get to parity in a more efficient way than like precision parity. We haven't quite figured out yet. We're still working on that part because it's not monotonically increasing. But yeah, I would kind of consider the post hoc correction type models for that, or approaches for that.
So actually, I have a couple of questions, and if there are no more right now in the Q&A. So one question is, particularly in policy, there are a lot of policy. When we make policy, it's not once and done decision quite often. You actually have to repeatedly make decisions, and the subsequent decision is based on the outcomes of the previous one, right? So a lot of the equity analysis and the solutions do not take that into account. You essentially say, okay, here's the equitable and fair solution or model, done. But by doing something, in one way now, that makes implications for next decision. So how do you consider that, address that, deal with that in any framework?
Yeah, no. So that's two things there, right? One is, regardless of sort of fairness, like anything, right? That's just true for whatever. Even if we are just generalizing for efficiency, we have to sort of figure out how do we generalize over time. And So one thing, there are two things we can do, right? One is we can do our training validation splits over time in the past, and sort of that's useful, but not enough, because that sort of tells us how robust our models are in the face of policies changing, not us changing the policy, but the policies changing. Elections happen, governments change. Some governments care about people, some care about money, some care about neither. And so that's something we, at a minimum, we can do is check robustness of. So when you're doing model selection, do you pick the one that's highest mean, or the one that's more robust, or the one that's more resilient to the certain types of changes like COVID? But then the second part is much harder and almost impossible without actually running trials, is how do you, when you change the data, when this recommendation that you help these people, if that gets taken, that changes the distribution of the data that's generated. And so the bias starts changing, and that's something we're working on right now, because now is the time when we've had some of these systems deployed for long enough that we can do that, right? Because this can't happen in a lab. This can't happen on a data set. It has to happen on this loop that people are taking live action based on your recommendations. You're getting that data back, you're giving them. So we're just getting to that part where we're looking at these dynamics changing over time. When we actually look at the bias thing, we actually see if we correct for bias at time t, there is, we test correction on t+1, but we have to adjust it at each timestamp. And so that's kind of what we typically do, but it's not, it's messy because it has to be done in the wild, right, as opposed to on a computer only.
Thank you. There is actually a quick question follow-up to the previous one from Dale Kuss. Can you give a 1 or 2 sentence explanation of what a post hoc correction is?
Yeah, so a very simple approach, and there are different versions of it, but a very simple approach is, let's say that you are selecting 100 people. So you have a model that's giving you a ranked list of 10,000 people, and your goal is to pick 100 from the highest risk, right? So your baseline approach is pick the top 100, and you calculate your precision. This correction one says, I want to pick 100 that gives me as high precision or accuracy as possible, but I want to make sure that my recall or sensitivity, right, for white and black is equal. So you basically separate the white and black people in that list and start picking them in a way. So you pick the top 1 from here and maybe top 2 from here, and you say, okay, now I have 3. What is my recall for each group? So you can basically, you're treating those 2 models as that ranked list as a collection of different lists from different groups that you want parity on. And then so it's a very simple algorithm, except it's the one that's most, it assumes that your ranking is somewhat correct. And it turns out in practice, our rankings are fine. Our within group rankings are fine. Our across groups are what's messed up. And so by separating them into different groups from the single ranking, we can then pick and choose which ones we combine to create our new list of 100. And there are other versions of it. So there's a paper a few years ago by Cynthia Dork, who's at Harvard right now, where they actually build composite models, where they say, we're going to build a white model and a model just for black people. We'll generate those predictions, and then we'll combine them in this way. And when they do that, actually, when we actually replicate their work, we find that the power is really coming from, in most cases, from this combination and not from the separation. So that's kind of a simple, and again, if you email me, I'm happy to send you a pointer to a paper that kind of talks more about that.
Thank you. Well, I'm gonna ask one more question, and if we have more, we'll continue until 1:30 at half hour. Otherwise, we'll wrap up. So the question, what I really like about the work that you do and that you presented is a lot that it is not descriptive or forecasting. So a lot of the work in machine learning and data science is about descriptive prediction, sort of who are the people who are, you know, likely to high risk of recidivism, who are the students who are likely to at a high risk of dropping out of high school or not succeed in undergraduate programs, or who are the people who are at higher risk of diabetes. And your work is very much focused on interventions to change the outcomes. You've alluded to it a little bit of how you choose the set of interventions that are possible, right? But that is really the key part of how do we decide of what are the knobs that we can actually.
Yeah.
So can you talk a little bit about that?
Yeah, that's a really good distinction, right? So what I sort of, I've been taking shortcuts, at least for now. And the shortcut is I'm working with people who understand interventions, who've been doing them, who are experts at them, they understand the people they're trying to help. And I'm just sort of helping them point, like, okay, go there, and you know, nudging them to kind of like point them to the people, and then they do their job really well. The mental health outreach team is amazing. They care about the people they're helping in Kansas, and they understand their needs. And if I can just connect them to the right people, things work out. That's not always the case. An intervention might not be effective for certain people because it's never been tested on high risk people. It's been tested on average, right? But the other thing is, you might have, as you said, like, so there's a project we're doing in Portugal with their employment agency, where we're kind of helping a counselor and an employment counselor connect this person who's filed for unemployment with their many training opportunities that exist. Which one should I recommend them? And so in that case, it's really not about, like, it's just too many of them. There are a few hundred available, and for each person might be eligible for 50 of them. I don't know the impact on this person of each of them to best recommend the right one. And the problem, or not the problem, the challenge with doing that analysis is, you know, the model that you're building changes from probability of risk to probability of change in risk conditioned on intervention A, change in risk condition intervention B. So you basically build intervention models, right? And people have started doing it. Like, the first time I built them at scale was during the elections in 2012, where yes, we want to predict who's going to vote for us or not vote for us, or vote or not vote, but we also want to predict who's persuadable, because that's where we're going to spend most of our money, is in persuading people. So we wanted to figure out change in probability of voting for us given the intervention. And over there, we had the resource to actually run large scale experiments. So we actually collected data for that model by running experiments. We persuaded people, and that became the label for the machine learning model. This person was persuaded, this person wasn't persuaded. So my model was, and in some marketing, that's called uplift models. And the idea is, you know, again, you're predicting the change in outcome as a result of intervention. Then you pick the one intervention that gives the highest, then you kind of run an optimization on top of that, right? And in a lot of the projects that I'm talking about, the first pass, we didn't do that. The second pass, so then this Johnson County thing, that's what we're going to do next, is try to build these models for effectiveness of intervention condition on sort of the characteristics of the person, so we can give them a new intervention or focus on the old ones. But that's a really important area, but that can't be done with observational data easily. You have to actively be able to run experiments to do that, which again takes time and effort and trust.
Thank you. So there's another question. Well, Andreas, yes, the talk is recorded and it will be posted on TDAI speaker page, which I will type the link in a second into the answer box, available for everyone. So there we go. It's now answered. The question from Sam Malloy, also from Battelle Center for Engineering Policy. Could you comment on training efforts at Carnegie Mellon University that focus on the intersection of policy and data science? Status quo in many places is a choose your own adventure approach. Have you had success with a more integrated training model?
I mean, I'm biased, so I think we've had success, but also I don't think it's just me. I think it's other people who've done an integrated. So I used to be at University of Chicago for many years. We had a joint computer science and policy master's program that we started in 2013. I think it was successful. CMU has had one for longer, and Georgetown started one a couple of years ago. There are other places that are, other versions of similar. I think they're successful because I think they're more successful than the choose your own adventure, because a joint thing is not taking a bunch of computer science classes, taking a bunch of policy classes independently. And I think the challenge is that when you start a new program that's integrated, just the practical logistics and financial nature of these things, you can't create too many new classes because it's a small program. So you often sort of like have cobbled these things together, but as these programs sort of mature, new classes get created, new experiences, whether it's project-based. And so I think that's the point we're at right now, is they're all these programs are kind of trying to figure out how integrated they really are within a class rather than kind of in the curriculum. But I've seen in a few different places that it's resulting in people who are going on to do the type of things that we want them to do, the types of jobs, and they seem to be doing well in those places. So whether it's selection, they're selecting themselves, or whether it's the program, I think that the outcomes are at least they're encouraging right now.
Thank you. And with that, Ray, this has been a fantastic talk and a conversation starter for sure. I'm sure these conversations will continue. I know I will continue our conversation that's been going on for about 10 years. Thank you very much. And I hope that you will have an opportunity to come and visit us in person. It's not that far.
Yeah, exactly. We're right here. So no, thank you very much for inviting me. And this was fun. So hopefully I'll see you in person soon.
Indeed. Thank you. Okay. And for everybody else, the recording will be posted on TDAI's speaker series webpage, available from tdi.osu.edu, as well as the TDI YouTube channel. Thank you for joining us. And let's do social good with data science.